This lecture is on the Introduction to Graph, Part 1. Hello everyone! So far in this series on data structures, we have talked about some of the linear data structures, like array, linked list, stack, and queue. In all of these structures, data is arranged in a linear or sequential manner. We can call them linear data structures. And we've also talked about tree, which is a nonlinear data structure. Tree is a hierarchical structure. Now, as we understand, data structures are ways to store and organize data. And for different kinds of data, we use different kinds of data structures. In this lesson, we are going to introduce you to another nonlinear data structure that's got its application in a wide number of scenarios in computer science. It is used to model and represent a variety of systems, and the data structure is graph. When we study data structures, we often study them as mathematical models. Here also, we will first study graph as a mathematical or logical model. Okay, so let's get started. A graph, just like a tree, is a collection of objects or entities we call nodes or vertices, connected to each other through a set of edges. But in a tree, edges are bound to be in a certain way. In a tree, there are rules dictating the connection among nodes. In a tree with n nodes, we must have exactly n-1 edges, one edge for each parent-child relationship. As we know, an edge in a tree is for each parent-child relationship, and all nodes in the tree, except for the root node, have exactly one parent. In a tree, all nodes must be reachable from the root, and it must be one possible path from root to a node. Now, in a graph, there are no rules dictating the connection among nodes. A graph contains a set of nodes and a set of edges, and the edges can be connected to the nodes in any possible way. A tree is a special kind of graph. Now, graph has been studied extensively in mathematics. In computer science, we basically study and implement the same concept of graph from mathematics. The study of graphs is often referred to as graph theory. In pure mathematical terms, we can define a graph using something like this. Graph G is an ordered pair of a set V of vertices and set E of edges. Now I'm using some mathematical jargon here. Ordered pair is just a pair of mathematical objects in which the order of the ordered pair matters. This is how we write and represent an ordered pair. Objects separated by comma in a parenthesis. Now, because the order here matters, we can say that V is the first object in the pair and E is the second object. An ordered pair AB is not equal to BA unless A and B are equal. In our definition of graph, the first object in the pair must always be a set of vertices, and the second object must always be a set of edges. That's why we are calling the pair an ordered pair. We also have the concept of an unordered pair. An unordered pair is simply a set of two elements. Order is not important here. We write an unordered pair using curly braces. Since the order is not important here, pair A and B is equal to BA. It doesn't matter which object comes first and which object is second. Now, I have a graph drawn here on the right. This graph has 8 vertices and 10 edges. What I want to do is give some names to these vertices because each node in a graph must have some type of identification. I am naming these vertices V1, V2, V3, V4, and so on. And the naming is not indicative of any order. There is no first, second, or third node. So this is my set of vertices here, is this. We have 8 elements in the set, V1, V2, V3, V4, V5, V6, V7, and V8. So this is my set of vertices for this graph. Now, what's my set of edges? To answer this, we must first need to know how to represent an edge. An edge is easily identified by its 2 endpoints. So we can just write the names of the 2 endpoints of an edge as a pair, and then it can be representation for the edge. But edges can be of 2 types. We can have a directed edge in which the connection is one way. Or we can have an undirected edge in which the connection is two-way. In this example of graph that I'm showing here, the edges are undirected. But if you remember the tree that I had shown earlier, then we have directed edges in that tree. With this directed edge that I'm showing you here, we are saying that there is a path or link from vertex U to V. We cannot assume that there is a path from V to U. This connection is one way. For a directed edge, one of the points would be the origin and the other would be the destination. For our example, origin is U and destination is V. A directed edge can be represented as an ordered pair. Now, if the edge is undirected, the connection is two-way. An undirected edge can be represented as an unordered pair. Because the edge is bidirectional, the origin and destination are not fixed. We only need to know what 2 endpoints are being connected. So now that we know how to represent edges, we can write the set of edges for this graph here. We have an undirected edge between V1 and V2, V1 and V3, V1 and V4. We have one between V2 and V5, V2 and V6, and one between V3 and V7. There's one between V4 and V8, V5 and V8, V6 and V8, and V7 and V8. So this is our set of edges. Typically, all edges would be either directed or undirected. That's good for part 1. In part 2, we will be looking at the types of graphs and what applications we can use for graph. Until next time, see you.